do apologize. Thank you, Professor Nishimori. Are we now picking up the sound better? Good, excellent. I shall give my introduction again. I'll be talking about the second order catalysts, which we've been looking at primarily numerically in my research group, which serve the purpose of enhancing these perturbative gaps, and I'll explain what I mean by a perturbative gap in a minute or two. And we're using this maximum independent set problem as a toy to try and elucidate some of the physics of what is going on. Okay, so if you're trying to make a quantum annealer with some speed up to find the ground state of some problem Hamiltonian, you need to solve a bunch of different technological problems. You need more coherence, you need more qubits, you need them to be well connected, you need to be able to program the qubits accurately. But if we fast forward to a world where you've solved all these technical problems, there are still some fundamental problems that may need solving. And in particular, how do you stay in the ground state as your system traverses through the gap minimum, or equivalently at the phase transition? And there are various suggestions for doing this. I quite like the idea of real-time feedback, but that's very difficult to achieve on these timescales. You might try inhomogeneous driving or counter-diabatic driving. What I'm going to talk to you today about is the use of catalysts to get you through this gap minimum. So as I said, there's been a number of different flavors of this work in my research group. And a couple of these have appeared on the archive in the last couple of weeks. Firstly, I'm going to talk about Luca Nutricati's work. Luca is in the audience here, and he'll be giving a poster on this work tomorrow, or you can look at this archive preprint. And what Luca has done is take 10,000 randomly generated Eros-Renyi graphs, and here he's plotting on the x-axis the minimum gap of these randomly generated graphs without a catalyst. On the y-axis, the minimum gap with this XX catalyst applied. And you can see that if you're above this red line, that means the catalyst is having a positive effect on enhancing this gap. And you can see in particular the hard problems with small catalyst-free gaps, you get an enhancement of the gap of 2 or 3 orders of magnitude. So speak to Luca or see his poster tomorrow to learn more about that. Something else that's been going on in my group in collaboration with Sugata Bose's group in UCL is this work by Rupayan Ghosh. And again, here's the archive preprint. And Rupayan will be giving the online INQA seminar on the 29th of October. So do tune in to hear that if you can. And again, so here's a random graph instance. And what Rupayan has been doing is looking at the XX catalyst, but also looking at the third order XXX catalyst. This particular example where he's plotting the energy gap during the anneal as a function of the annealing parameter. If you just have the conventional X driver, you have this minimum gap and phase transition here as an annealing parameter of 0.998. If you apply an XX catalyst, you increase this by a few orders of magnitude, but still it's there. And you completely eradicate this if you apply this yet higher order, third order XXX catalyst. So I urge you to look at our archive preprints to learn more about that. So what I'm going to talk about today is I'll tell you in the rest of this presentation what these perturbative crossings are. I'll introduce this weighted maximum independent set problem. I'll talk about initially some work which we did a couple of years ago now on the XX catalyst and how that enhances the gap. And then the new stuff, I guess, is more recent work on what I call different flavor catalysts like XY and YZ and so on and so forth. And then I'll round off with some conclusions. So most of the work that I'm presenting in what follows is done by my PhD student, Natasha Feinstein. She's writing up her thesis at the moment. We had a paper appear in Phys Rev A about a week ago now, and also we have another paper on the archive, and that'll talk about these XX catalysts. Okay, so first of all, introduction to what a perturbative crossing is. I can't see the time. I can now see the time. So a perturbative crossing is an avoided level crossing late in the anneal. So typically in a hard problem, you might have eigenenergies, eigenstates of your problem Hamiltonian at very similar energies. And then as you apply the transverse field, these eigenenergies may cross at an avoided level crossing late in the anneal when your transverse field is small. And this gives you a gap minimum, which is very hard to get across. So that's what I mean by a perturbative crossing, and it means that you may end up in an excited state at the end of the anneal unless you go slow. So digging slightly further into this, where most of what I'm saying, I guess, was introduced in this excellent paper by the chairman of this session, jointly with Vicky Choi, a number of years ago now. And following their approach, you can write down the annealing Hamiltonian as a sum of your problem Hamiltonian, and then treat the driver as a perturbation on the problem Hamiltonian. So if you do this, you find that the lowest order non-zero terms in your perturbation expansion are the second order terms. So here we're plotting the eigenenergies as a function of lambda squared. And the case lambda equals 0 corresponds to here, and you might have some problem ground state and first excited state close in energy. And then as you introduce the driver by moving along this lambda axis, these states may cross if the slopes are different in these two dependencies for the ground state and the first excited state. So this gives you this perturbative crossing here, which will be difficult to get through in an annealing experiment. So how do we remove this perturbative crossing? What you want to do is change the slopes of the dependencies of these two eigenenergies on the perturbative parameter lambda, or lambda squared more accurately. So if I can move the dependence of the ground state down, as shown in blue, and the orange first excited state up, I can eliminate this perturbative crossing late in the anneal. And you can find out more about this in Natasha's paper in Phys Rev A. So that's what we're hoping to achieve in order to remove these perturbative crossings. So we can start doing some perturbative analysis of this. So what I'm going to do is, first of all, we have to perturb the problem Hamiltonian with the driver with some perturbative parameter lambda. And then we're going to add a catalyst to this. This might be an XX catalyst, or it could be some other term. And we're going to analyze this by considering the effect of the catalyst as being a perturbation on the already perturbed Hamiltonian, where that perturbation is from the driver. So there's two perturbations going on, the driver with weight lambda and the catalyst with weight mu. And to first order, you can write down your perturbative expansion like this, where this is, again, this is some eigenenergy that's already perturbed by the driver, and then we add the perturbation here from the catalyst term. And then you can re-express this using these computational basis states B and C. Now, if your catalyst is this XX interaction, so your catalyst Hamiltonian now is XX, then this simplifies things further. What you find is that you can sum over all pairs of basis states which are coupled by the catalyst. So in the case of the XX interaction, this is all states that are Hamming distance 2 apart from one another. And then you get this term here. And what you can show is that this is always positive for relevant states. And by relevant, I mean that when state A, the state A is a local minimum, and states B and C are low in energy, close in energy to that local minimum. So given that all these summand terms are positive, which you'll have to take at face value here, then it's kind of clear what you need to do in order to remove this perturbative crossing. So if you're adding some new couplings to the ground state, you need to make sure that the sign of this interaction is negative, which pushes this blue line down. And or if you add new states which couple to the first excited state, you want this JXX term to be positive. So this gives us two distinct ways of trying to prevent this avoided level crossing from happening by coupling new states either to the ground state or to the first excited state. Okay, so we're going to look at, that's our perturbative analysis of how you introduce a catalyst perturbatively. And now I'm going to talk about this weighted maximum independent set problem, which is our tool for looking into some of this. And in particular, we're looking at this tripartite weighted maximum independent set problem. So thankfully, Konstantin did introduce the maximum independent set problem. In the unweighted version of this, the challenge is to find the largest subset of some graph where no vertices within that subset are directly coupled to one another. So in this particular case here, that would be this orange subset G1, which has a bigger membership than the other independent sets G0 and G2. Now, in the weighted maximum independent set problem, we assign weights to each of the vertices. And the challenge then is to give you the maximum, is to find the maximum weight within a subset where no members of that subset are directly connected. Okay, so that we've set this up in this tripartite case because we have 3 local minima corresponding to the 3 graphs G0, G1, and G2. And we set it up in such a way that we can vary which one is the global minimum by adjusting the weights on each of the subgraphs. And furthermore, we can adjust the value of the minimum gap. So it's a sort of tunable hardness problem where we can adjust the value of the minimum gap by adjusting the weights and the number of the vertices in each subgraph. And that should be pretty clear just from this picture. You can fairly straightforwardly map this onto the Ising model. And I should point out that many of the ideas, again, come from Vicky Choi's paper 4 years ago. So some technical details of what I'm going to say next. The ground state is always going to be the set containing all vertices in this blue set G0. And we penalize including vertices from 2 or more subgraphs in your candidate independent set just by putting very high weight edge penalties on all the edges. And by choosing this 3, 4, 2 subgraph sizes, so 3 in the ground state, 4 in the first excited state, and 2 in the second excited state, what we achieve is that we have a perturbative crossing between the ground state and the first excited state. And the second excited state we use just as a kind of control because it's not involved in this perturbative crossing. So there's some technical details. And the other technical detail I need to give you is what the schedule is. So we have the usual model schedule, if you like, where the driver decreases in amplitude linearly during the course of the anneal, the problem increases linearly, and the catalyst has this parabolic form given by these expressions here. Okay, so first of all, we're going to look at gap enhancement with the XX catalyst. And the basic idea is shown here. So if we add an XX catalyst to the subset that corresponds to the ground state, then we're adding new couplings between states that are close in energy to the ground state. So we're sort of attacking the ground state, if you like. And just as a technical detail, in fact, what Natasha does is not just attach a single XX, but in what follows, we attach an XX interaction between all pairs within this ground state subset. That doesn't change any of the underlying physics, but it does help the numerics because it's a much more symmetrical system. So we can apply the XX coupling in the ground state, or we can apply it to the first excited state. And again, if we apply it here, we will add new low energy couplings to states for the first excited state. This will have a different effect, as we'll see. And again, actually what Natasha does, or has done, is attach this XX interaction between all pairs within that G1 subset. Okay, so here's the numerical result, just from diagonalizing the Hamiltonian here. So we're plotting the minimum gap at any stage during the anneal as a function of the strength of the catalyst, and the different colors correspond to putting either the XX catalyst in G0 or G1 or G2 according to the coupling. And you can see this exactly follows what we're expecting from our very simple perturbation theory, at least in the case of the XX catalyst. So if we're putting the couplings in the ground state, we want the sign of that catalyst interaction to be negative. And if we're putting the couplings in the first excited state, we want the sign to be positive. So this exactly matches our perturbation theory. And just for completeness, if we put the couplings in the second excited state, which does not take part in this perturbative crossing, then approximately nothing happens. So far so good. We can enhance the gap quite significantly by putting an appropriately located and appropriately signed XX catalyst into our graph. Okay, so now some more recent work that Natasha has done, where we ask the question, what happens if we change the flavor of the catalyst? So you can pick any 2 of these letters, any 2 of these Paulis, and they will give you different effects, as we'll see. So the basic idea is that, of course, an X Pauli gives you a spin flip, If you've got a Y Pauli, that gives you a spin flip and a phase change. And the Z Pauli just gives you a phase change. So depending on which Pauli you're using, you can get different phenomena. And the question now is, how does that affect our perturbative analysis? So this follows a very similar line of reasoning from what I was saying in the XX interaction case. So we start off by perturbing the problem Hamiltonian with the driver with some amplitude lambda, some perturbative parameter lambda. And then we perturb that combined problem and driver Hamiltonian with this catalyst term HC with a perturbative parameter mu. And it's a very similar sort of analysis, so I'll cut to the chase. You basically have to sum over this interaction here over all pairs of basis states that are coupled by the catalyst. Now, in the case of the YY interaction, which is what I'm looking at here, forgot to mention that, sorry, you have now this prefactor which appears in front of this operators, which can take the value of plus or minus 1, depending on which states you're coupling and how much phase you're adding from that YY interaction. And this is distinct from the XX catalyst, where this prefactor was always equal to 1. So in fact, I left it off the previous expression. So now when you're doing the sum over these basis states, it's a more complicated situation in which some of these terms, some of these pairs of states will add with positive prefactor, and some of them will add with a negative sign in front. So it's going to be not so straightforward as just picking the sign of JYY, and that is indeed what we see when we do the numerics. So here's again the result of the exact diagonalization on this tripartite maximum weighted dependent set graph. Here's the gap minimum as a function of the catalyst strength. When it's a YY catalyst now, again, we can place it in the ground state, which gives us this rather funky looking blue expression, or in G1, we get this orange line. And again, it's clearly not as straightforward as when the summand in your perturbative expansion is always positive. So the phases are confusing the matter for this YY interaction. Now, what about the full zoology, as I call it? What happens when I look at all the different types of catalysts I could apply? We've seen XX already, that's the blue line. And here I should say I'm applying these interactions to the ground state subgraph, which is the blue subgraph over here. And we've seen YY, which is in orange, and there's a whole bunch of stuff going on. Some of it matches the perturbation analysis, some of it doesn't. But of course, maybe this is just an academic discussion, because if we know the ground state a priori, and so we know where to apply this particular catalyst term, then we've solved the problem a priori, so there's no point in doing this. So perhaps what's more interesting, to me at least, is what if we put the couplings in the first excited state subgraph? So now here, if we put an XX interaction in the first excited state, we've seen this data before, and all the other terms basically do very little apart from the ZZ interaction. So if we have a ZZ catalyst that we apply to the first excited state subgraph, and we pick a negative sign on that catalyst strength, we get a significant enhancement in the gap minimum. So I'm just going to reach my conclusions now, which is trying to understand what's going on and how we might actually exploit this. So for XX catalysts, first of all, we've shown that we need to add a positive amplitude XX catalyst to the first excited state. That will give us a gap enhancement. So how can we use this? I mean, we don't know a priori what the first excited state subgraph is for a complex problem in general. But you might imagine you could run the annealer with no catalyst. You could assume that the identified lowest energy solution you end up with is in some way partaking in the perturbative crossing, might be the first excited state. And so you add XX couplers to the graph that you've identified from your first anneal run, and then run the annealer again. And you could do this iteratively in order to improve your solution. Of course, the problem here is that XX couplers are hard to engineer. There are proposals out there for doing it, but it is a hard engineering problem. So why don't we just use a ZZ catalyst? Because ZZ, in the flux qubit context, certainly exists already. It's an inductive coupler. And we showed that by adding a negative catalyst strength ZZ coupler to the first excited state, we can enhance the perturbative gap. So I've already said this is going to be easier to engineer than the XX interaction because it exists already. And I should also draw your attention to this paper by Albash and Kowalski, where they were looking at a single Z catalyst, which is kind of biasing your solution towards the ground state solution. And that's kind of similar but different. Of course, we're applying a ZZ catalyst, which one imagines is biasing your solution towards solutions which are ferromagnetically ordered. And so I think it's fair to say that the effectiveness of this approach is going to depend upon the structure of the problem Hamiltonian, i.e., is this ferromagnetic catalyst term biasing towards the solution? So I've slightly gone over time, but I've reached the end of my presentation. Finally, I just conclude with some acknowledgements. Natasha did most of this work, also Luca, Rupayan, and some other people. And you can look up more on this work in these references shown here. Thank you very much for your attention.
Questions from audience? Nick.
That works better. Okay. Very interesting stuff. So you can see this reduces the gap. Have you looked at what this does more in a diabatic regime, or do you have plans to look at that?
Yes. So if you look at this conveniently located reference to the Physical Review A paper, there is long discussion about how you can use these XX catalysts to introduce a second gap in the annealing process. And that does allow you possibly to go into the diabatic regime and take a shortcut through the first excited state to the ground state at the end. Now, for lack of time, I deliberately ignored that particular topic, but it's certainly feasible. Again, if I'm honest, it's not clear to us now how general that approach is, but it certainly works very well in the context of this weighted maximum independent set problem.
Any other questions? Yes. Yes.
Thank you for your nice talk. And if my understanding is correct, all your result is based on perturbative analysis. So perturbative analysis. So yeah, I think it works well for the system which has minimum energy gap at close to their final classical points, but the system is not necessary to have its minimum energy gap close to. So for such a case, do you have any idea to estimate the validity of your method or your result?
Yes, that's a fair comment. I mean, the perturbative analysis only works if we have a perturbative gap minimum. In some of the instances, and I'm afraid I can't remember which, but when I showed you the full zoology, some of these, I forget which, I apologize, really do not match the perturbative analysis at all. Details of this, I'm sure, will be in Natasha's thesis when it appears. If you look at certainly the XX interaction does match very well with the perturbative analysis. And that's backed up by the numerics, I guess. So we do the perturbative analysis. Certainly in the case of the XX interaction, it matches that very well when we do the numerics. But in other cases, not so much. I agree.
Thank you.
We have time for one more question. Yeah.
Yeah, thank you. So if I understand correctly, you basically are like in a problem where you know a lot already in terms of like ground state and versus state. But have you considered what happens, or have you some intuition if you basically randomize this approach and throw in couplings of random strength between random qubits, for example? Or what happens on average, or if there's
yes. So in terms of the XX interactions, that's essentially what Luca's poster is about, where he generates random graphs of the Erdos-Renyi and the Barabasi-Albert type, and then does some brute force statistics on when does that help, when does that not help, summarizing lots of numerics in one sentence. It helps most of the time, but not necessarily. But yeah, so take a look at Luca's poster tomorrow. And then also Rupayan's paper, which is on the arXiv, is again random graphs with yet higher order catalysts, XXX and higher.
Okay, yeah, thank you then.
Okay, thank you very much. Let's thank the speaker and all the previous speakers now. And